2-3 মিনিট ওয়েট করি। 30 হয়েছে এখন দেখছি।
ঠিক আছে কৌশিক।
হ্যাঁ, ভালো আছেন তো?
হ্যাঁ হ্যাঁ, শুনতে পাচ্ছ?
হ্যাঁ, শুনতে পাচ্ছি।
ওই তো অরিন্দম বাবু আছেন।
হ্যাঁ হ্যাঁ।
হ্যাঁ, ওই 2-3 মিনিটের মধ্যেই জয়েন করবে আবার অনেক।
না না, ঠিক
হ্যাঁ,
আছে ঠিক আছে ঠিক আছে।
ঠিক আছে। সমীরণ দা, আপনার টকের পরে পারলে আপনার এই স্লাইডটা একটু আমাদের শেয়ার করে দেবেন।
আচ্ছা আমি তোমাকে আজকেই করে দিতে হবে কি?
না না,
ঠিক
আজকে
আছে।
করতে হবে না, আপনি
আচ্ছা
পরে করে দিলেই হবে 2-3
আচ্ছা,
দিনের মধ্যে। ঠিক আছে।
তোমাদের কি পরীক্ষা টরীক্ষা হয়ে গেছে?
না, পরীক্ষা হবে এবার, ফাইনাল সেমিস্টারের পরীক্ষা আছে এবার, এই
মানে
জুলাইয়ের এন্ডে হবে।
তার মানে তোমার সবাই আগস্টের মধ্যে যা হবে, আগস্টের মধ্যে রেজাল্ট বার করে দেবে?
হ্যাঁ, আগস্টের 6 তারিখে বোধহয় রেজাল্ট বার করতে হবে, এরকম একটা কিছু আছে।
ও বাবা, তোমাদের
ওরকম
কি
একটা
যাচ্ছ না বাড়ি থেকে?
বাড়ি থেকে।
আর এমনি মানে টোটালি বন্ধ ইউনিভার্সিটি?
না, টোটালি বন্ধ নয়, মানে কিছু অফিস কিছু সিলেক্টেড জায়গায় খুলছে, ভিসি অফিস, রেজিস্ট্রার অফিস তো খোলা আছে মাঝে মাঝে, কন্ট্রোলার সেকশন তো খোলা আছে, কারণ
না,
পরীক্ষাগুলো
আমাদের তো
কন্ডাক্ট করতে হবে।
কন্ট্রোলার অলমোস্ট নিজেরাই। হ্যাঁ অরিন্দম বাবু।
হ্যাঁ, আমাদের ওই পরীক্ষা আমাদের হয়ে গেছে, থার্ড ইয়ার এমএসসি পিজিটি
আরে
সব হয়ে গেছে।
আমাদের এই শুরু হবে তার মানে
আচ্ছা আচ্ছা।
সময়ই নেই একদম, তার মধ্যে মানে এত কম সময়ের মধ্যে খাতা দেখা আর এক মানে এই কম্পিউটারে
হ্যাঁ
খাতা দেখা মানে মাথা ধরে যায়, মানে ঘাট সোজা করে বসে বসে
হ্যাঁ,
ঘরটা
ঘাড়ে ব্যথা হয়ে যাচ্ছে তো।
আর ব্যথা এক্স্যাক্টলি।
অনলাইন।
আমাকে অনুপদাও বলছিল, কালকে অনুপদা ফোন করেছিল আমাকে।
হ্যাঁ,
হ্যাঁ হ্যাঁ
স্ক্রিনে পেজ স্ক্রল করে করে খাতা দেখা, আর অনেক লেখা
হ্যাঁ
স্পষ্ট আসে স্ক্যান করে, খুব
এবং
অসুবিধা।
এবং হাত ব্যথা ঘাড় ব্যথা দুটোই হয়ে যায়।
হ্যাঁ হ্যাঁ,
হ্যাঁ, এই মানে চ্যালেঞ্জিং ব্যাপার।
আর কাকে কি নম্বর দিচ্ছি মানে কোথায় ভুল দেখতে পাচ্ছি একটু নাম্বার কমিয়ে দিচ্ছি, কিন্তু সেটা আর মনে থাকবে না, পরে যদি কেউ চ্যালেঞ্জ করে
হ্যাঁ
গেল।
সেটাই সেটাই। আসলে ওদিকে একটু ডিলেড হয়েছে বলে এদিকে একটু ডিলেড হচ্ছে বলে।
না ঠিক আছে ঠিক আছে।
হ্যাঁ, আমাদের আগের টকটা ডিসকাশন পরে একটু একটু 10 মিনিট ডিলেড হয়েছিল, সেই জন্য বোধহয় একটু সবাই জয়েন করতে ডিলে হচ্ছে।
মোটামুটি সবাই বাংলা বোঝে তো?
না না,
না,
অনেকেই আছে অবাঙালি।
আচ্ছা আচ্ছা
অনেকবারে এ থেকেও আছে, বিভিন্ন জায়গা থেকে, এবার রাজস্থান, কেরালা, মহারাষ্ট্র, অনেকেই আছে,
আচ্ছা
গুজরাট, বিভিন্ন জায়গা
আচ্ছা।
থেকে আছে।
প্রবাবলি অন্য কান্ট্রি থাকতে পারে। বাবলু, রেজিস্ট্রেশনে অন্য কান্ট্রি ছিল কি?
না না না,
না না না, ইন্ডিয়ানই সবাই।
ওকে, ঠিক আছে। আমি 1 মিনিট দেখে নিয়ে তবে স্টার্ট করি নাকি অরিন্দম
হ্যাঁ
দা?
হ্যাঁ হ্যাঁ হ্যাঁ,
হ্যাঁ, ওকে।
6টা 5-এ, 6টা আমার ঘড়িতে 4
ছটা।
4 হয়েছে, এখন 6টা 4।
হ্যাঁ হ্যাঁ, 4 হয়েছে, রাইট।
হ্যাঁ।
হ্যাঁ, ঠিক আছে।
স্টার্ট করলে আবার আস্তে আস্তে সব জয়েন করে যাবে। স্টার্ট করে
আচ্ছা, ঠিক আছে। Well, good evening, everyone. So we are now going to start this second session, second talk, and that will be delivered by Professor Samiran Ghosh. He's from Department of Applied Mathematics, Calcutta University, and he is now a professor there. And he did, just to say about a brief profile of Professor Samiran Ghosh, he did his PhD in science from Jadavpur University in the year 2001. And before that, he was joining this applied mathematics department. He was joined as a reader in that particular department. And before that, he was lecturer as well as senior lecturer in the Department of Mathematics at Government College of Engineering and Textile Technology, Berhampur, Murshidabad. And his research interests are different purpose of mathematics, like, for example, nonlinear wave processes in plasmas and complex, better to say dusty plasmas, also in the general approaches of nonlinear dynamics as well as stochastic processes. So today he will be delivering a talk on the stochastic processes and perhaps differential equations on stochastic processes. So I request Professor Samiran Ghosh to start his talk.
Thank you, Kausik, and thank you, Arendra Babu, for giving me this opportunity to share something regarding stochastic process and stochastic differential equation. So let's start. Actually,
স্টার্ট।
just a minute. So I am just trying to start.
Yes, it has come.
So it is visible. Kausik?
Yes, visible, very much visible.
Okay. So thank you everybody. Basically today I will discuss just introductory part of a stochastic differential equation along with stochastic processes, and mainly one-dimensional stochastic differential equation. So before starting, we will recapitulate something regarding probability. As you know, in the classical probability theory, what we have learned in our honors or the definition of probability from classical one is m by n, like from that, where the major defect, rather main defect of that definition was that the prior assumption was the all the outcomes are all the quantities or all the events which we want to get are equiprobable. So to overcome this definition, frequency definition came, then statistical regularity, and there was also a mathematical flaw, and after that axiomatic definition of probability came, and it was introduced by Kolmogorov, a great mathematician. So according to Kolmogorov, first of all we have to know the basics, simple one or two slides regarding this. To sigma, let us consider a random experiment. You all we know what is random experiment. Random experiment is the kind of experiment whose outcomes are known, but we don't know what outcomes will occur at what time, at when. So consider a random experiment, and we considered all the outcomes of omega of that random experiment. And among these outcomes, those satisfies some axioms which are already given. 3 axioms are called events. Actually, in the classical definition, the problem lies in the to define the event. Not all outcomes are events. Only those outcomes which forms a sigma algebra, we can call this as events. Because according to Kolmogorov, probability measure means we can define a probability only on an event. So first of all, we should know what is event. Again, I am telling, among all of the outcomes, which satisfies but which belongs to a sigma algebra is called the events. And then corresponding the probability which we know, the probability measure, usual axiomatic definition format, the probability measure. Then we consider the probability triplet. These are all simple basics, where omega is the total sample space, U is the sigma algebra, and then on this we define a probability measure. So that is totally, we call this a probability space. And any outcome that belongs to U, scriptic U, we call is event. And probability of A, that means we can define a probability on an event A. And another thing, we later we will see that this definition, we will usually use this definition, almost surely convergent. Actually, in a sequence of random variables, xn, omega n greater than equals to 0, converts a random variable, let's say x omega, almost certainly or almost surely or with probability 1 if probability limit n tending to infinity xn omega is equal to x omega is equals to 1. That means almost everywhere except some set, which in probability sense we call this a probability, in measure theory we call this a set of measure 0, except the outcomes belong to that, this condition holds. So we usually denote it as A dot S dot or sometimes A dot C dot. So that means almost surely with probability 1. Then the random variable, all this we know. Here the one condition is that the x is a mapping from omega to Rn. We know in this case it is a n-dimensional random variable. And for each B, it is the Borel set. Borel set denotes the collection of all Borel subsets which is the smallest sigma algebra subsets of R containing all open sets. So here the measurability means for any given two numbers A and B, in a simple way we can say that for a given number A and B, they are the set of all outcomes small omega for which A less than equals to x omega less than equals to B is an event. So in measurability, in the sense of this, rather the measurability condition means that given to real numbers A less than equals to B, the set of all outcomes omega for which A less than equals to x omega less than equals to B is an event. This is the concept of measurability of a random variable. Then now we come to the stochastic process. A stochastic process is a family of random variables, and here the t belongs to t. Usually we take t as a time. First of all, I will say that most of the cases we will define on 1D, not multi-dimensional. I will clarify something regarding multi-dimensional in some special cases, but most of the cases we are dealing with one-dimensional. The random variables here is indexed by t, where t belongs to capital T. For of real line, t is usually we call time, two index sets T, where T is discrete, then the process will call a discrete parameter stochastic process. If T is continuous, means T 0 less than equals to T less than infinity, this process is called continuous parameter stochastic process. Basically, a stochastic process is a function of two variables. One is T, time belongs to capital T, another is omega, belongs to capital omega. All these are simple nomenclature, rather notations. For fixed T, we denote it as T dot T, a dot for a variable. Here T is fixed, it is a random variable. Or for fixed omega, X dot, where T is a variable, omega is fixed for a certain event. We measure the random variables for a certain event. X dot omega is a function of time, which is called a realization of the process, or a sample function, or a trajectory, or a path, and usually denoted by xt. Here are some sample paths of a stochastic process. These two stochastic processes for sample path, here T is fixed, but omega is different. But stochastic sample paths are like this two. The main point, another point I want to mention, that in case of a stochastic process, the sample space of sample paths, it's create a sample space. What I want to say is that we have already seen in probability to define probability measure, that we can only define probability measure of a only on a event. So not all outcomes of a random variable are events. So in that sense, if we consider a finite dimensional random multi-dimensional random variables, so when we want to see that process, means X, which contains several paths, sample paths, xt1, xt2, xtn. So question is that if all these sample paths by which we can define, rather we can measure a probability, we can define a probability measure for all these sample paths in case of finite dimensional. In case of a two-dimensional, ordinary case, one-dimensional or two-dimensional, it can be done. That means what we know in case of one dimension, we can extend it to the two dimension. But in case of n dimension, to overcome this difficulty, again, Kolmogorov gave a theorem. Here I am not stating the theorem. I am not stating the statement in a theorem form. The main point, what was mentioned by Kolmogorov, that we can extend it to a finite dimension for say n dimension if the distribution functions satisfy two properties: symmetry and consistency. So according to Kolmogorov, if the sample space of a stochastic process satisfy the distribution function corresponding to the sample space of a stochastic process, satisfy two conditions, symmetry and consistency, then we can easily extend it to a multi-dimension. So that is one of the main point, particularly in case of stochastic process, because in general it is a multi-dimensional process. Next we come to some special stochastic process, special case of stochastic process. First of all, stationary stochastic process. In case of stationary stochastic process, the joint distribution of xt, say at time t1, at time t2, time tn, this joint distribution of this, and say tau consider, and interval, fixed interval tau. So the distribution function x at t1 plus tau, t2 plus tau are same for all tau belongs to t. Then xt omega, the stochastic process, is called the stationary stochastic process. Interestingly, in case of a one-dimensional distribution, in case of n-dimension, this can be written in this form, in general form. And in case of one-dimensional, the distribution will be time independent, because at at t equals to t1, the distribution function as t1 plus t2 at t equals to t1 plus t2, the distribution function both are same. So in that sense, in case of a one-dimensional stochastic process, rather in stochastic process, the probability distribution is time independent in case of stationary stochastic process. Whereas in case of two-dimensional probability distribution, in this case, we can write the distribution function. Finally, we can see that we can write the distribution function in that sense. The time difference of these two, if we start, say, probability x t1 omega is less, as we define the definition, distribution function, we write in terms of probability, is equals to, according to the definition, is equals to this t2, means at t equals to t1, the probability distribution function is given by the left hand side, and at t equals to t2, the probability distribution is given by the right hand side, where we write t2 in this form, t2 minus t1 plus t1. Now we call t2 minus t1 at tau. So if we start, so this will becomes this part. So if we start, say at t1 equals to 0, and keeping tau in that form, so finally we get the two-dimensional distribution function will be a function of t2 minus t1, means will be a function of tau. Another special types of stochastic process is the wiggly stationary stochastic process. Sometimes it is also called the wiggly stationary in broad sense. If it satisfies two conditions, mean is independent of time, it is finite, and the RTS means covariance between two processes at time t and at time s, where s is less than t. In that case, the covariance function will be function of t minus s. So in that case, there is another process, another stationary process we call ergodic. If its expectation mean can be written as a time average of the sample function. Now stochastic process with independent increment. Independent increment means, say we consider xt omega stochastic process, and at time t is equals to k, at time t is equals to tk, let us start from t is equals to t1 to t equals to tk, rather t equals to t0 to t equals to tk. Then the differences xtk omega minus xtk minus omega, this is also a stochastic process, means I want to say that xtk omega minus xtk minus omega is also a stochastic process. Similarly, xtk minus 1 minus xtk minus 2 omega is also a stochastic process. So increment means there tk minus 1, tk minus the stochastic process at tk minus 1, it's an increment. These are also increment. If these increments are independent, then the process is called the independent increment stochastic process. So from the definition, it follows that the stochastic process whose independent increment is specified, rather described by the distribution function of, it is clear from the definition that xt omega minus xts and xt0, most of the cases by definition xt0 is taken as the 0. T0 is less than S, less than T. Another is that the stochastic process is said to be orthogonal if the increments are only mutually alkorelated, means covariance of these incremental stochastic processes is equals to 0, where I not is equals to 0. Another independent stationary increment, where already independent, means in the increments are independent, but at the same time this process is stationary. So a stochastic process is said to be a process with independent increment if its incremental distribution, incremental the process that are independent random variable, and the distribution of xtk omega minus xtk minus 1 omega are function of tk minus stationary process. The we can distribution function in case of two-dimensional, that it is basically at time t is equals to 0, rather at time t is equals to t1, we can write the distribution function in terms of that will be a function of difference of these two increment of time. And these two, rather the first one, a stochastic process whose increments are orthogonal. So in that case, we can write function will be a covariant function, will be a covariant function of minimum of t and s. So it's a one character of a stochastic process with orthogonal increments. And the another property is that x2 omega, a stochastic process, x2 omega be a stochastic process with independent stationary increments. In that case, this is one of the most important property of a stochastic process. Variance function, rather variance is a function of t. Actually, this property differs from a deterministic case to a stochastic case. We know actually variance, what do we mean? Variance is the variations from a mean path, if I think in terms of path. So since it is a function of time, so these variation functions will fluctuate with time. So that is one of the important characters, but rather that introduces the stochasticness of the system. Whereas in case of deterministic function, this is purely constant. So in case of latter, we will discuss mostly on the independent stationary increment processes. So in that case, these variance part play an important role. Moreover, this will differ the deterministic case and stochastic case. So there is a this is an example of a stochastic process. Say xt omega is equals to a omega cos 2 pi t plus b omega sin 2 pi t. This process is weakly stationary stochastic process. It is given that these two random variables are uncorrelated, their mean 0, and variance is sigma square. So in that case, we can easily calculate, but others calculate that covariance function is a function of t minus s. So this is an example of weakly stationary stochastic process or stochastic process in the sense of in the broad sense. Another process is there, which is the well-known Markov process. I think most of us are very much well acquainted with this process. So basically, first of all, I am telling you the Markov property. Markov property is basically a memoryless property. This property tells us that the future state depends only on the present, not on the past. Similarly, the present state depends only on the just before the present state, not on the previous one. So from the definition point of view, the conditional probability we call P is the rather later we will discuss. We will tell what is P. P is the probability at time tn the process takes the value xn, whereas it start at t1 time with value x1 dot 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 tn minus 1 time with value xn minus 1. That is depends. This conditional probability depends only on just the before one process, value of the before one process. So then this process is called the Markov process. So it is a memoryless process, and this conditional probability is called the transitional probability. Means I can transition from state n minus 1 to state n, and using the product rule, chain rule, we can factorize this form which we have written here. Probability of xn at time tn, xn minus 1, this can be written in this form. So the important part of these two important parts, first of all, it is a memoryless process, and second one is that this process is completely defined if we know the value of these last two probabilities. Probability probability at t is equals to t2 given, but rather it is happened that t1 probability at t is equals to t1, and the probability of the px1 t1 where t1 is less than t2. So if we know the value of this probability, we can, this process is completely defined by this chain rule. Here we consider an example. Say zt omega is to the vector stochastic process, two-dimensional, xt omega, yt omega. The form is this form, in this form. So for simplicity of notation, but rather from the above relations, we can say at t is equals to tk, the value of x is x tk omega. So for notational simplification, we use that x tk, and this is equivalent to x tk minus 1, t k minus 1 at k minus 1, and similarly y tk. Then from these two, we can derive that xk at k, yk at t is equals to tk. These two value, sample value of the process zk is completely known if we know the sample values of k minus 1. That means k is depend on only on k minus 1. So this is this is a property of Markov process. So we can say that this vector stochastic process is a Markov process. Another stochastic process is a Gaussian process. It is very much well known, but here just I want to say something. That's why I have given this. We know that normal distribution of 1D probability function, if xt follows normal or rather Gaussian distribution, then 1D probability distribution can be written in this form. But in case of multi-dimension, xt, where xt takes the value xt1 omega, x2 omega, xtn omega, is called the Gaussian if the joint distribution of these forms are normal or Gaussian distribution. This can be written is matrix. Since it's a multidimensional, we can write it in the form of matrix form. So here is another example why extension of n-dimensional extension of probability distribution or extension of probability density function is required to define a finite dimensional stochastic process, because stochastic process in general, stochastic process is a multidimensional process. It takes so many sample paths at say at t equals to t1, t equals to t2, t is equals to tn. So define a stochastic process fully, we have to know the distribution, rather characters of that joint of the character of the joint distribution function of the made by these processes at t is equals to t1, t is equals to t. Because if we want to get some information from the stochastic process xt omega, then the main thing is that first of all we have to ask which one occur. Means, say I am taking the value, I consider a stochastic process xt omega, and it contains the values xt at t is equals to t1, t is equals to t2, t is equals to tn. So if I take that stochastic process, then we have to know the whether at t is equals to t1 happen t is equal, what was the character of the path by other process at t is equals to t1, t is equals to t2, and t is equals to tn. So to define a stochastic process, extension of multi-dimension of the distribution, probability distribution function is essential, and Kolmogorov did that. One of the example of bivariate normal distribution, we did it in our honors, at least in our time we did this at our honors courses. It is just kind of example. Next, the calculus of usual ordinary calculus which we have learned, and in case of stochastic calculus is slightly different. Here we will say, means here in case of stochastic calculus, we will define continuity, differentiability, everything in terms of mean square, in terms of expectation of square of that random variable. Because here everything is average. Everything is average means we will when we will see the example, then I will clearly explain this. So this is one of the difference of ordinary calculus to stochastic calculus. So that's why we need to know these definitions. So mean square continuity of a stochastic process. A stochastic process xt omega is said to be mean square continuous at t is equals to t naught if limit h tend to 0, almost same, but expectation of x t naught plus h omega square is 0. But in case of t is equals to t naught, we can write it as in that in this form, and usually we write is in this form: limit in mean L dot I dot M. This implies limit in mean. So whenever we see this, then we can understand that this continuity with respect to the mean square continuity. Here another definition is that stochastic process is said to be second order when its expectation of x square is finite for all t, and for such second order process, the mean function is mean value function, rather mean function. Mean value function will be a function of t, and covariance function can be written in this form. And here one theorem is that a second order stochastic process xt omega is continuous in the mean square at t is equals to t if and only if the mean value function mt is differentiable at t is equals to t, and covariance function is continuous at tt, because covariance function is defined usually this ts. So at t is equals to tt, this covariance function is continuous. And similarly, mean square differentiability, same process, same way, limit h tending to 0, expectation, here is the operator, expectation operator, is, we say this part means usual definition of from the first principle definition of dy dx, left hand side, and right hand side we usually denote it as x dash, so write it here, and square in the sense of mean square equals to 0. So in this case we say that our stochastic process is a process which is mean square differentiable. Similarly, there is also a theorem Second order stochastic process is differentiable in the sense of mean square at t is equals to t naught if and only if the mean value function mt is differentiable at t is equals to t naught, which belongs to t, and the generalized second order derivative of the covariance function exists at t is equals to t naught. Means derivative in the case of derivative, in case of continuous, covariance function will be continuous at t equals to t in the sense of mean square, and in case of differentiability, the covariance function has to be differentiable at t is equals to t naught. Then mean square integrability. Similar way as we did in case of Riemann integration, consider a partition, same way, but same thing we have to define in the sense of, as we have said, that here all the calculus means continuity, differentiability, and integrability will be done in terms of mean square. So definition will be like this: limit usual Riemann, but taking the expected value by expectation. Taking the expectation of these two different square. If this is equals to 0 as max delta t tending to 0, that means capital N tending to infinity, partition, total number of partitions is n, starting from 0 to n. Then we call that we say that the integration I, where I a b by omega, where a to b xt omega dt is Riemann integrable. Means a stochastic process is Riemann integrable in the sense of mean square. Just remember it, a stochastic process is Riemann integrable in the sense of mean square. Later we will say that in case of stochastic differential equation, this will not happen. Then we have to define another calculus. As usual, this is also a second order stochastic process. In case of second order stochastic process is Riemann integrable if mean in integration of mean and covariance function, integration of the covariance function exists. Then we call that the second order stochastic process is Riemann integrable. Another process here we want to know, because first of all, to frame a stochastic differential equation, we need to know, at least in the preliminary stage, we must need to know the Wiener process, rather Brownian motion, and then we will see the white noise, because these two play important role to define to construct a stochastic process, a stochastic differential equation. That's why I am discussing this. Wiener process, rather Brownian motion, it is also called Wiener because Wiener give a rigorous mathematical treatment, though Einstein give represent it in terms of a delta correlated force, so which will lead us to determine the Avogadro number, but it was first mathematically treated by Wigner. So that's why this process is called Wiener process. It is the characteristics of this process is that it was observed by Robert Brown. He observed highly irregular, rapid, and non-interacting motion of particles suspended in a colloidal solution. And as it was observed by Robert Brown, so this motion is called Brownian motion. And the particles follows these characteristics, the particle which follow these characteristics is called the Brownian particle. So these two are the pictures of paths of a Brownian particle, and here without any mathematical treatment we can say one interesting thing, that the path of a Brownian particle is continuous everywhere, but is nowhere differentiable. So we consider the left hand side. Say all these x-axis is the t-axis and the y-axis is the x, means process path axis, sample path axis, and the differences we call this as delta t. In case of delta x, we call it delta x. We see the totally irregular, rapid, and non-terminating motion. And if we see this, we look that the path, sample path is continuous. But if we want to consider the slope, it will like a plus delta x by delta t or minus delta x by delta t, is varying at random. So at delta t tending to 0, so delta x tending to 0. So the slope cannot approach a definite value. So from this, the conclusion is that the Brownian motion is continuous everywhere, but nowhere differentiable. Actually, this approach, this physical approach, on the rather observational approach, on the basis of this particle path, the conclusion was drawn by Chandrasekhar. A famous article that was published in Astrophysical Journal FJ. So this is one of the example, a function which is continuous everywhere but nowhere differentiable, is the Brownian motion, the path of a Brownian particle. So the randomness of Brownian motion means that it does not behave well enough to be integrated by traditional method. These are the main important things which we will introduce in the stochastic differential part, differential equation part. Again, the randomness of the Brownian motion means that it does not behave well enough to be integrated by traditional method. Now we definitely, as I have already told you, that this Wiener process and then the white noise will play an important role, rather decisive role, to at least at the preliminary stage to construct a stochastic differential equation. So we need to know the mathematical formulation of Wiener process. But you can call it as Brownian motion. A stochastic process xt omega is called a Wiener process if it satisfies the following properties. First of all, omega naught, at t equals to 0, at t equals to 0, we start at omega process, the value of the process takes the value 0. Then omega t is a normal or Gaussian process with 0 mean, and RTT is equals to, RTT means variance basically, sigma square t. Here sigma square is the variance parameter. It's a constant, positive constant, variance parameter. Most of the cases we take it as 1. And then WT has almost surely continuous trajectory. We know everywhere continuous. Almost surely, say here in the sense of probability, which we have already defined, I have already defined, the index almost surely. So is continuous. And it has independent stationary increment. So the statistical distribution of omega t plus s minus omega s is independent of s, means it will define is equivalent to the distribution of omega t. So this is the part, since it follows the Gaussian, and in case of these two difference, we can write it in this form. One thing, I have underlined this point too, because if we see, the path, this path is, we have already discussed that this path is continuous everywhere, but nowhere differentiable. But to make it mathematical formulation, how we infer that this path follows normal distribution? So that's why here we discuss this. because of the randomness, of the collision, simple here we consider 1D motion of a Brownian particle. We can take it as symmetric random walk along a straight line. What is the symmetric random walk? Let us consider this figure. Say we consider a path like a straight line, just this path, and the middle part is the middle one. Symmetric random walk means what is random? Symmetric in the sense, if I go one step forward, then the probability of the one step, unit step forward, is equals to the probability of one step backward. So symmetric in that sense, if I go one step forward, and then symmetric in the sense at the same time I have to go, but rather I have already went the path one step backward. So if we according to the nature of the Brownian motion, so that's why we call take it the path path of the Brownian particle, rather the Brownian particle motion, we consider it as a symmetric random walk along a straight line following a large number of small steps. Finally, it will give the whole path of length delta x. Now we consider a random variable ik that represents a random variable at kth step, such that this is the character of a symmetric random walk. The unit step means delta x step forward is probability half, is total is 1, and the one step backward, the probability of one step backward, unit step, rather here delta x step backward is half. So in that sense, this is a symmetric random walk. Since collisions are independent, so these random variables are independent set of random steps. So of being ik is 0. Now it is not an assumption, rather it is the outcome of the random walk problem. If we calculate the mean of jk, simply what will be the expectation value? Delta x into half plus minus delta x into half, so that it will give you 0. And in case of variance, what will be? Delta x plus delta x square into half plus minus delta x square into half, so that it will give you delta x square, and we call it delta x square, delta k square, since the random variable k. And displacement after finite time t means after n step, we call it xn is equals to summation of this, such that mn means expectation of xn is in a similar way 0, and the variance of xn clearly derived here is n sigma k square. We call it sigma n square. Now there is a theorem of Lyapunov. According to the Lyapunov theorem, delta kj's be independent random variable with mean 0, variance say sigma k square, and xn equals to this with mean 0, variance sigma n square. Now according to the Lyapunov, if there exists a delta positive such that this condition hold as n tending to infinity, then xn minus mn by sigma n tending to 0 are standard normal distribution. So in our case, we can easily substitute this value and see that this follows standard normal distribution. So the path which we have observed in case of Brownian motion, which is continuous everywhere but nowhere differentiable, follows normal distribution. At least here we have proved it for one-dimensional case. and there are properties. Expectation of this is 0. These are standard. Anyone can try to solve, because you know the normal distribution, so and the stationary property, so you can easily derive this. Similarly, in case of covariance function, for a winner process, it will be minimum of st, because which we have already seen that in general, for a independent stationary increment stochastic process, covariance function is it will be the covariance function of minimum of t and s, and in this case, since it is proportional to t, means s or t, so which is minimum, that will give you the result. So all these are simple proof. Now the differentiability of winner process. Since the Brownian particles, the motions of Brownian motion is continuous everywhere but nowhere differentiable. So since we want to formulate this Brownian motion mathematically, so winner process is also a non-differentiable process, which we have proved it here. Easy proof, limit of h, expectation of this is square is h in the sense this is nothing but the increment t plus h minus t. So increment is h, expectation of square, so this is proportional to sigma square t. We have already seen that variance function for independent stationary increment, variance function ft is equals to sigma square t. Here we take sigma square, the variance parameter is 1. So some mathematical simplification, and finally we see that this does not exist. In terms of covariance function, we have already seen from the theorem that for a second order stochastic process, the derivative of the generalized derivative means del 2r by del t del s, this will define. If it exists, then we say that that process is differentiable. In case of covariant winner process, del r by del t, as we have seen that this will be the minimum of any s and t. So if we derive it, so you will get this. The nature of this derivative is a Heaviside unit function in s. So to study the existence of the differentiability of the winner process, if we derive this in terms of s, this will, that means a kind of Heaviside function, rather Heaviside unit function. We want to derive, find the derivative of the Heaviside unit function. This will give a Dirac delta function, delta t minus s. So W dot means derivative of winner process is a delta correlated process. Next, we want to know the integrability of Brownian motion. This is one of the important part of a stochastic process. We have already seen that sample paths of Brownian process, rather Brownian motion, are nowhere differentiable. That is, any sample path changes its shape in the neighborhood of any time in a completely non-predictable fashion. I'm not giving you the details of this proof. So unbounded variation of linear sample path means if we take the, we know the bounded variation property. So supremum of this is equals to infinity. It is not bounded. Almost surely, means with probability 1. Here I want to say something that Taylor, which I have not mentioned here, Taylor have shown that in case of p-bounded variation, the Brownian particle means Brownian particle, rather winner process, can be integrated in terms of Riemann-Stieltjes integral, usual ordinary integral, but Riemann-Stieltjes ordinary integrals, ordinary means Riemann-Stieltjes integrals, but there is a typical example which very frequently occur in stochastic process. that is not exist. Means if p is less than equals to 2, Brownian motion has a bounded variation, p variation for p greater than 2, not for p less than equals to 2. But there is an example which frequently occur in stochastic differential, the stochastic process, which is where in that, for that example, rather that for that process, for that case, it is not Riemann-Stieltjes integrable. So Taylor showed this. So in general, due to the unboundedness of the path, sample paths, it is not integrable in terms of our ordinary integral. Then we come to the definition of white noise. Say xt omega is a stochastic process, continuous parameter. I am only telling you the discussing here the continuous parameter stochastic process. So according to the continuous parameter stochastic process, we know that the Wiggly stationary continuous parameter stochastic process, we know that the covariance function is a function of t minus s. We write it in this form, and finally take we write tau is equals to t minus s. It is symmetric and non-negative. There is also a proof for the symmetricity, for symmetricness and the non-negativity of this covariance function. Then we define this. Rather, we take the Fourier transform of this, and we write it in this form. So where f omega is the distribution function and phi is the density function. Thus, for Wiggly stationary continuous parameter stochastic process, phi omega is called the spectral density of this. Phi omega is called the spectral density of xt omega. Now, what is white noise? Now, a Wiggly stationary stochastic process is called white noise if the spectral distribution, rather spectral density function, is given by phi constant. Spectral density function is constant. Why it is called white noise? Because in case of white noise, all amplitudes are equal. Means it absorbs the whole spectrum of it absorbs all the spectrum. In another way, amplitudes are equal. Here, since the spectral density shows the same character, is equals to constant, so it is termed as white noise. There are other is also there, color noise and different types of noise. I think Kaushik has discussed already. So my concern is regarding this simple white noise. So for a continuous parameter white noise, we can, according to the previous definition, we can write it is in this form. So we see that this covariance function is for a white noise is nothing but a delta function. Means this process is also a delta correlated. So from these two property, the white noise, the covariance function of a white noise is a delta correlated process, is a delta function, and we have already seen that the differentiation of a Wiener process is also a delta correlated function. So from these two, we take, rather we conclude that we conclude that, sorry, this will be xt, sorry. If xi is a white noise, if we call this xi as white noise, sorry, there is a typos. So xi, if we call this xi as a white noise, so this is dwt by dt. This implies xi dt is equals to dwt. So this is one of the most important part in the latter cases. So this is a kind of observation, rather simulation result of Gaussian white noise. Now we consider the stochastic differential equation. We know in case of ordinary differential equation, all we know here, just I am for the sake of introduction, I take this one. Say x naught equals to x zero, the initial condition dx dt is equals to ftx. So the result is like this. So whatever be, if we consider one-dimensional case, whatever be the solution of a differential equation is nothing but the integration. Ultimately, we have to do some integration. So this is the solution. And if we look the path, but rather trajectory, so it is like this. But in many applications, in most of the experimental values, but in case of communication system, if I want to send some signal, there are so many other noises, means other signals are there, they will create problem and create noise in the original system. In case of feedback control theory, so in most of the cases, the trajectory looks like this. So to interpret this trajectory, we are reformulating that differential equation in the following form. It was written as in terms of ATXT. Here we take AT is equals to FT plus HT xi t. Later we will define it. So then we can write it as instead of x, we take it as capital X to introduce the stochastic process. dxt dt is equals to ftxt plus ht xt xi t. Here ft, ht and xi t are given function of t. However, the one-dimensional noise process, however, to know the xi t, we have to know the probability law of the xi t. That is our introduction as a noise. So we have already discussed regarding the characteristics of this white noise. So in this case, we rewrite, rather we replace this xi t in terms of Wiener process. So finally, the differential equation introducing xi t as xi t, here xi t is taken as white noise, is right in this general form. And this term, the first ft xt omega dt plus dt xt omega dwt, the first term is called the except dt term, deep term, and the second one is called the diffusion term, where omega denotes xt omega is the random variable, because this is the initial condition, x naught omega is s naught with probability 1. Here the classification are there, when it is called the linear, when it is called homogeneous, and there is also a condition like our usual ordinary differential equation. It is called exactness. It is It is called the exact differential equation. Exact stochastic differential equation when this condition holds. Now we will come to this solution part. Just like our ordinary differential equation, we write this solution in this form. Regarding the first part, 0 to t fsx dx, this will not create any problem. We have already seen that this is Riemann integrable. That's why in that when I had discussed regarding Riemann integrability, I had pointed out that. So this part is Riemann integrable. No problem, we can integrate this part with our usual knowledge. But the problem creates in the second integral. What is this? Gx omega is okay, but what about this dwx? Because here this is the Wiener process. So due to the randomness, due to the non-differentiability nature, randomness, this cannot be Riemann integrable or usual our known ordinary integral. With the help of ordinary integral, our known ordinary integral, we cannot integrate this part. Even the Riemann Stieltjes integral is not also valid for this case. So we have to redefine the integral, and Ito, and there are two senses. So many senses are there. More popular are one. Ito and Statanovich. So Statanovich introduces a concept of integration mean square in the sense of mean square, which is known, which is very famous in stochastic differential equation. Stochastic integral is known as Ito integral. Say we want to integrate the second part, 0 to t gt omega dwt omega. We assume the gt omega is only changed at discrete time points ti. What does it mean? Means we consider a piecewise random step function given by this, and at the same time there is also a theorem, any random step function which can be considered as the limit of a sequence of piecewise random step function. So keeping in mind, we define this integral and consider a sum just like Riemann sum. What is this? Look, this one. We consider this GTI1, GTI minus 1, omega TI omega, WTI omega, WTI minus omega. We consider this Riemann sum S. And we define a random variable. Rather, Ito define a random variable. We call this the Ito integral of the stochastic process is if limit n tending to infinity, this is equals to 0, just like which as we have defined in case of mean square integrability of a stochastic function. So in this case, stochastic integral is also a random variable. Again, the only thing is that in case of stochastic integral due to Ito, we define this Riemann sum in this form, and if this limit n tending to infinity means if this equals to 0 according to the mean square integrability condition, then we call this is Ito integrable, and we can integrate this stochastic solution part of the stochastic differential equation. Now there is interesting result. There is a difference between the ordinary calculus and stochastic calculus due to Ito. We consider GT is equals to C constant, just writing this, use this formula, and finally get this one. Just C into WT omega. Now, this is the most famous example. We consider GT omega is equals to omega T omega. This we can write it 0 to T, WT omega, WT omega dWt omega. Using the definition limit tending to infinity, instead of GT omega, we write it WT minus omega and calculate this. Now the mathematics is there and expectation values. Everything is given in this slide. Everything is given. So finally, what I want to say that finally, what we get? We get, using all these things, we get omega w square by 2 minus t by 2. This is the difference. If we want to integrate this part in our ordinary calculus, the result is omega w square by 2. But here another extra term is there, capital T by 2. So this part shows that the usual rules of differentiation is not, rather we have to reformulate it, is not valid in case of Ito calculus. These are the properties of Ito calculus, and I am not giving the proof of this. In any textbook you can get it. Now another thing is that stochastic differentiation rule. Most of the stochastic process are not differentiable, just like Wiener process. So we always write it in our infinitesimal changes of the process, d omega t instead of d w dt. So these are the simple changes. Xt is a stochastic process. At time t, t plus delta t is given by so at t plus delta t, it will be x t plus delta t. So increment of this is given by this, and in case of infinitesimal changes, we can write it as dxt is equals to xt plus dt minus xt. Now we consider the rule, usual rule, plus minus rule. Now we come to the point which will differ from the ordinary differentiation part. We consider the product of these two, xt and yt, and after using just simply using this definition, we finally get this one. So xt dt, xt dyt plus yt dxt, this part is okay. Is from our knowledge of ordinary usual calculus, but this is another part which have come due to the stochasticness of the process. So keeping in mind to overcome, rather to justify this, Ito introduces the lemma, which is well known for as Ito's lemma. Before that, why it is happening? In usual calculus, we know all this thing. Just keeping it is usual calculus for small delta 6 delta x. We usually neglect this term, higher order term, and finally we get this. But in case of stochastic process, Ito introduces, rather keep this term half, which we have omitted in our, which we usually omit in our usual calculus, usual differential, usual calculus. But in this case, keep it. Ito kept it due to the fact that, say, we consider xt is equals to wt, which is the winner process. Now, if we take this, so in this case, this will be dwt square. It looks like a second order. Basically, since I have already told that in case of stochastic process, everything will be, we will think everything in terms of expectation. So in this case, this is equals to dt. We write it as dwt square, where wt is the winner process. We write it as dt, and this is 0 in sense of expectation. Here it is given e of dt square. We can write it in this sense, and finally we get dt. So this part plays an important role in stochastic process, and if we keep this term, so then all integral values, the results of integration for stochastic process and others, we can usually recover this. Now Ito's lemma. This is another way to solve a stochastic differential equation. So we consider a stochastic differential equation in this form, and another process yt, and we want to write yt in terms of this, like L1. And the assumption, what was the assumption? Assumption is that phi t is continuously differentiable in t, and twice continuously differentiable in x, and so that we can write it in this form. So usual procedure, we expand in Taylor series expansion, and keeping the term d or wt square, but not the higher order term dt w2, where just think dt square, it become tending to 0 more rapidly. But in case of w square t, since it is equivalent to dt, rather equal to dt, so we keep it here. And finally, sorry, we get this omitting the higher order term and keeping the dwt square term, which is equals to dt. We finally get this, and these are the form of when we rewrite the stochastic process, the stochastic differential equation in terms of yt. new introduced variable. So this will be like this, and the term here half of phi xx, this term is called the Ito correction term, since it does not occur in the deterministic case. Now we consider the previous great example 0 to t wt dwt. Now we try to find out this value in terms of Ito lemma. We consider yt is equal to phi t. The trick is here. I am giving you a trick. Whenever you take, if you want to solve a first order, simple first order stochastic differential equation in terms of Ito's lemma, better you take the variable yt as the classical result one, classical one. Means 0 to t wt dwt. In case of classical calculus, it is wt square by t. So we take it. We take yt is equals to wt square by 2 and xt is equals to wt. We write it in Ito's formula, and finally we get wt square by 2 minus t by 2. In a similar way, we take this t as twt. Bypass, if we take the bypass, finally we get the result. Oh, sorry, I am not giving it the bypass formula. It's okay. Simply take yt is equals to twt and use the Ito formula. You will get Ito lemma. You will get the value. Similarly, the other one. Now, the solution of stochastic differential equation. We consider stochastic differential equation in this form and introduce the variable yt is equals to phi ts, which is equals to ln st. Actually, if we divide, just think in this, we can think in this way. If we divide st, and take integration, left hand side will be ln st. So we take yt, the new variable, as ln st. Then introduce, use all the steps of Ito's lemma, and finally we get the result. Similarly, there is also an example, and other example here it was in both sides, it was st, in three sides st, but here little bit different. Dxt is equals to mu xt dt, d simple dwt. So in this case, we take yt is equals to e to the power minus yt xt, just like our classical, without this term, without this dw term, the solution looks like this in case of classical calculus. We take this as yt and apply the Ito lemma and finally get this result. Another is there, Ornstein-Uhlenbeck process, which describes the Langevin. This is the mathematical form of Langevin equation. The solution of this equation, we can also find the solution of this equation in this form also. Now the properties of solutions. Properties of solutions means in most of the physical system which we usually we encounter in real life, solution is okay, but since we are dealing with stochastic process, means stochasticness is there, so we have to calculate the expectation and variance of that solutions, and that expected value or variance means variations of that solution will give us some physical insight of the process, rather, or the physical insight of the dynamics. So to do this, we consider the usual way, the stochastic differential equation, and we write the solution just like linear. We get this and take, if this is the solution, we take the expectation of both sides, and m dot t means derivative of m means mean, p dot means derivative of y square variance with respect to variance. So we can take it, and finally in some cases we get a system of equation from where we can solve the we can find the expectation value and variances as well. Now, another example is that expectation of e to the power alpha wt is equals to e to the power alpha square by t2. Here we also use the Ito's lemma. Consider this yt is equals to this, and after using the Ito's lemma, form of Ito's lemma, we finally get this value. Now, one thing, this part value of expectation of 0 to t yt dwt equals to 0, you go back, if we look at the properties of the solution of Ito process, you will get this one. So using these properties, we can find the expected value of this. Similar with, we can find the expected value of e to the power minus omega t. It is another thing is that it is say a solution is given like this, and we want to find mean and variance. So it is one of the general case. From this we can find the expectation or variance of the function. Now go back to the Oster-Uhlenbeck process. xt, we know the solution is this, so find the mean and the variance, and from this, why it is the properties of solution, means the expected value of solution and variance of solution is important, because if we take this from if we find calculate this, from this we get limit t tending to infinity, mt is equals to 0, and variance is sigma square by 2 alpha. So we can give the physical insight of the process. Here for long run the process fluctuate around 0 mean, and the variance sigma square 2 alpha, it depends on the parameter, means higher alpha the lower the variance, and this obvious, since higher alpha the faster the process reverts back to its mean value. Means if we look back to the process, there is minus alpha, so higher will be the value of alpha, it will revert back to its drift away. First it drift way back to its mean position, because that is the drift term, and it follows the normal distribution. Similarly, Brownian bridge problem is one of the important problem. All these you can see in textbook also. So these are the variance and the mean value, and the path looks like this. And another, here I am just giving you some idea regarding the Stochastic. We consider that integral which we have already defined according to Ito. Here we write it is in this sense. The Ito integral is like this. Now here we assume that gt omega is an explicit function of wt omega. So in that case, Stochastic introduces an integral in this form, which we call it I Stochastic, limit in the mean delta x, delta max tending to 0, n tending to infinity, I tending this. Just see, instead of this omega, Stochastic took wti omega plus wti omega by 2. This is equivalent to this. Instead of this omega, we took this, and there is also example, and introduces the stochastic, another stochastic integral. The benefit of this integral is that this is nothing but this result of the stochastic integral is, as usual, our ordinary calculus, integral of ordinary calculus. Just like this. In case of Tito, we get T by 2, whereas in case of Satanovich, we get W square by 2. This is like our classical integral, classical calculus. So, thus in case of Satanovich integral, we can use it in formal rule, and formal ordinary chain rules also holds. But the restrictions is that Satanovich integral is only defined for explicit function of Wt omega, whereas the Ito integral is defined for functionals on this Wt omega, all form of Wt. And that show the Satanovich integral is defined for a much more restricted class of functions than Ito integral. And there is also an equivalence, a relation. There is also a relation between Ito and Satanovich. Satanovich showed that if this is continuous, g, function g is continuous in time and has a continuous partial derivative and satisfies this, then in the sense of mean square, Satanovich integral is equals to Ito integral plus sigma square by 2. Here sigma square is the variance parameter. And last integral is a well-defined Riemann integral of sample function. So here is the outline of the proof, very simple. Take the difference, use the mean value theorem, and use the property of this, you finally get this result. Now we consider an integral, differential equation. dxt is equals to xt d omega t plus sigma square by 2 dxt xt dt. And we know that in Ito sense, we take the integral of this, and in Satanovich sense, this we take the integral of this as Satanovich sense. We write this means we use the formula, and finally get this is equals to this. Now here I take this example because if this is the solution, then in sense of Satanovich, we get dxt is equals to xt dwt. That means if we compare these two differential equation, if we compare these two differential equation, we will see that this sigma square t xt is the drift term, and xt dwt is the diffusion term, which we have defined in the standard stochastic differential equation. So in Ito stochastic differential equation, we get both the term diffusion and drift term, but in case of Satanovich, we get only the drift term, now only the diffusion term. So this is one of the main difference. Now it's okay. So I am completing. I have tried, rather I will say I have tried to introduce, or rather I have tried to give you some flavor of stochastic differential equation. If anyone interested, you can see this references book. The first one is the book reference one is very good. Other is also very good, but the first one is also good. And for physical aspect of stochastic differential equation, Gardiner book is also very good. So you can consult. And lastly, thank you for bearing me. Hello.
Yeah, thank you very much. So it's a very, very nice talk and a very informative one. You have covered so many items in one particular single talk.
So actually, you know better. It is next to impossible to
Yes.
to complete, to discuss all the aspects of
Right.
the stochastic differential equation.
So yes, and of course, yes, you have started from the very, I should say, the very scratch part of this one, from the very beginning of stochastic process. Then you have tried to develop the ideas of differential equations of that one. So many things have been covered, and I got one question. Our one of the conveners, Dr. Bablu বিশ্বাস, has already raised one question, and this is about the dot, and it was cited somewhere in the beginning part of your lecture. And can Abdu please raise your question once again?
Actually, I have got it. While sir was defining the random experiment in stochastic process, in one slide I have got that notation, that is omega dot x omega dot, like that. Most probably I forgot.
Sorry, but some typos are also there. You are talking.
Okay, sir. There is another thing I have noticed that you have used L dot I dot M in place of limit. So, is there any significance or?
Actually, right. I have already discussed it. Again, I am telling you, L dot I dot means limit in min.
Okay. I missed it.
Actually,
Thank
it
you,
is a
sir.
convention to identify that all the limits are taken in the sense of mean square. So that's why the notation is like this: L dot I dot M, limit in min.
Okay. Thank you, sir.
Any further question? Participants, if you have any question, then please ask.
I just want to ask one thing, that I am a layman in this field. Is there any concept of stochastic ordinary differential equation or partial differential like that? No.
Yes. Actually, in the last slide, there was a stochastic partial differential equation. That is the great one known as Fokker-Planck equation. So here, just I have not discussed it. Just one or two slides is there. If you are interested, I can also.
Yes. Because for T1, T2, there may be stochastic partial differential equations will come.
Stochastic partial, and that was actually there is an equation. It's called master equation, and that is from in case of Markov process, there is an equation we can derive as master equation. There is also equation Chapman-Kolmogorov. So step by step from master equation using using Chapman-Kolmogorov theorem, then there is also called a Moal expansion, Moal cluster expansion, and introducing the Moal cluster expansion, we finally get the Fokker-Planck equation. So here, for the sake of just introduction, I took that one. Here I didn't show that one.
Thank you very much for your nice presentation. Many things we have learned.
No worries. Thank you. Thank you.
Welcome.
And any further question? No, it's one just particular question. That's not a question, perhaps a query. That can we have any resemblance between the fractal nature as well as the stochastic processes? Because in case of
to be very frank, I don't have any knowledge regarding fractal calculus, fractal. So I think, and one thing I can give you one thing, that in case of discrete stochastic process, maybe there is a connection, but I don't have any idea. To be very frank and honestly, I don't have any idea.
It's okay. As I just raised this question because in case of fractal also, kind of whenever we talk of a fractal curve, basically we consider this as a continuous everywhere, but differentiable nowhere. So this is the ideal definition is being provided for fractal curve.
So then definitely, very much application is there in case of fractal.
It should be, but I'm just looking for the connection. It's okay. Thank you very much for your feedback. Anyway, if there is no further question, then let us stop today's discussion. And this is the penultimate day. Tomorrow we will be having the closure day. This will be the last day for this particular workshop. So thank you very much, all the participants, as well as to the speaker, and who delivered this lecture very nicely. Thank you, Shomiranda.
Thank you, Kosik. Thank you, Arindam Da.
Thank you. Thank you. Thank you.
Thank you.
Okay, fine.
So okay, so we are.
So Kosik, দুজন কি বলছি সেটা হলো আমি 2-1 দিন পরে যদি দিই অসুবিধা আছে?
হ্যাঁ, ঠিক